Hi all, welcome to Ghiloo once again. So in this video basically I'll be continuing from question number 4 onwards of exercise 5.1. So in a similar way we need to prove here that the function fx equal to x to the power n is continuous at x equal to n, where n is a positive integer. So without any further delay, let's get started with the solution. So here, before starting, first let us write the function. So you can say that it is very evident that f is defined at all positive integers, because at all positive integers n, the value of fx is n raised to the power n, isn't it? So that is what I'm going to write now. And its value at n is n to the power n, for obvious. So you can see there is no need of proof here why n to the power n should be defined. It is very obvious. So where n is a positive number, obviously that for any integer, positive integer n, it would be defined. So obviously then limit of x tends to n f of n is equal to limit of x tends to n x raised to the power n, isn't it so? Okay, so this was to be x, so this is going to be n raised to the power n, because the function changes no definition, as well as there are no as such points of confliction. So therefore limit of x tends to a f of x is equal to f of n. Hence f is continuous at n, where n is a positive integer. Alright, now coming to the next question. So in question number 5, we have the function that has a change in definition before 1 and after 1. So it breaks at 1. We need to find whether it is continuous at x equal to 0, at x equal to 1, or at x equal to 2. So basically before proceeding into the normal solution, which we will anyways do, I am giving you a shortcut. If you are very proficient in making graphs, you can do it in just one line, or even you don't need to make one line. You can just visualize it and see. So if f of x is equal to x, what does that mean? Let us suppose this is our graph. I'm sorry, I'm not straight. F of x is equal to x. This is y equal to x. That is up to the point when x is equal to 1. So when x is equal to and less than 1, f of x is equal to x. But for x greater than 1, it is a constant function whose value is equal to 5. So obviously, since y is equal to x, at x is equal to 1, y would be equal to 1. But just after 1, the function assumes the constant value 5. So you can clearly see from this example that this function is continuous at x equal to 0, but discontinuous at x equal to 1, and once again continuous at x equal to 2, because alongside x equal to 2 in either of the side, it has no change in its property. Only at x equal to 1, the behavior of the function changes, and we can clearly see that we need to lift off the pen to draw this. So this is a very shortcut way in which you can even show that it is continuous. But continuing our old-fashioned way of finding limits and all, let us do it in that way as well. So we write the given function. Now at x equal to 0, it is very evident that function is defined at 0, obviously, because for x less than equal to 1 it is defined. So then we take the limit of x tends to 0 f of x is equal to limit of x tends to 0 x, because for x less than or equal to 1, the limiting value is x itself. So that is going to be equal to 0 for sure. Therefore limit x tends to 0, f of x is equal to f of 0. So we have ample amount of evidence to show that f is continuous at x equal to 0. So therefore f is continuous at x equal to 0. Now let us check the same for x equal to 1 in the same way. So I am not going to explain it so much because it's literally a waste of time. F is defined at 1 and its value at 1 is 1, because for x less than or equal to 1 we have the value of the function defined as x. So for x equal to 1 also we have f of x is equal to x. So f is defined at 1 and its value at 1 is 1. But now since the definition changes at 1, we need to check the left hand limit and the right hand limit. So now let us check the left hand limit. The left hand limit of f at x equal to 1 is limit of x tends to 1 minus f of x equal to limit of x tends to 1 minus left hand side of x means x is just less than 1. So the definition of function is x itself, that is equal to 1. Now the right hand limit, of f at x equal to 1 is limit of x tends to 1 plus f of x. Now just if the x exceeds 1, the value is 5, so the limiting value is actually is equal to limit of x tends to 1 plus of 5, that is equal to 5. So we can clearly see that limit of x tends to 1 minus, that is the LHL, is not equal to limit of x tends to 1 plus of f of x, that is LHL is not equal to RHL. So therefore f is not continuous at x equal to 1. Very similarly, let us check it for x equal to 2. At x equal to 2, f of 2 is equal to 5, because 2, since 2 is greater than 1, and f of x is equal to 5 for all x greater than 1. We can write it in this way also. We need not write it in a sentence, big sentence. We can write simply in a mathematical form. So then we have the limit x tends to 2 f of x. Since there is no change in definition along 2, so we can have it as simply limit of x tends to 2 5. Now since 5 is a constant, its limiting value is always a constant. So therefore limit of x tends to 2 f of x is equal to f of 2. You can clearly see that is what I have written. So therefore f is continuous at x equal to 2. Therefore f is continuous at x equal to 2, and that is what I concluded. So I have concluded its continuity at all the points in the function, and therefore the question is done. Now coming to the last question for today. So in this question we have to do a bit of reverse engineering. In all the previous questions we needed to check whether the given points at the given points function was continuous or not, but here the case is just opposite. Here we need to find all the points of discontinuity where f of x is given. So it is very evident, since it is a polynomial function, it is continuous at all the points where its definition is constant. So we can check the discontinuity only where its definition breaks. Okay, so let us do it step by step. Firstly, the given function is, now by now we are very clear that where it is a polynomial function, it must have to be continuous if its domain is constant, means it has no change in definition. So we have three cases: c is less than 2, c is equal to 2, and c is greater than 2. So for c is less than 2, f of c is equal to 2c plus 3, which implies that it is continuous for all c less than 2. For c greater than 2, f of c is equal to 2c minus 3. So it is continuous for all c greater than 2 because it's a polynomial function. Now for c is equal to 2, let us take the case of it. For c is equal to 2, let us check whether the limit exists or not. This is as simple as that. So for c is equal to 2, the LHL or the left hand limit of f at x equal to 2 is limit of x tends to 2 minus f of x, that is equal to limit of x tends to 2 minus, since before 2 the definition is 2x plus 3, that is equal to 2 into 2 plus 3 equal to 7. The right hand limit of f at x equal to 2 is limit of x tends to 2 plus f of x, that is equal to limit of x tends to 2 plus. Now at just greater than 2 we have the definition as 2x minus 3, that gives us 2 into 2 minus 3, that means 1. So as you can clearly see here that the LHL and RHL itself are different, that means the limit itself does not exist. Forget about continuity. So therefore it is clear that f is discontinuous at x equal to 2. Only at x equal to 2 f of x is discontinuous. Why? Once again let me be clear about it. We have three cases because the function itself is divided into three parts. For c less than 2, we have a constant definition. Since it is a polynomial function, 2x plus 3 is polynomial function, it has to be continuous. There is no other choice. Similarly, for c greater than 2, we have the definition as a polynomial function and hence it would also be continuous. But for c equal to 2, for a bit less than 2, for a value less than 2 we have different definition, for a value greater than 2 we have a completely different definition. So it was a point that was needed to check, and after checking we got that it is really not continuous because the limiting values are different. So it is not continuous. So in the next set of problems where this will be the type of the problems, we would be finding the discontinuity only at the points where the definition of the function breaks. That's all. So I hope you have no problem. If you have any problem, please feel free to use the comment section. We'll be starting from the next question in the next video. Thank you very much for watching this video.